this lesson is an introduction to harmonic motion. Now when we're dealing with harmonic motion, we have a spring, okay, which is attached to something that doesn't move, okay, so in this case a wall. And then on the other end of the spring, we have some kind of mass attached to it. Now we say that the spring has a constant, okay, which is called K. And when we're writing out an equation for the sum of the forces, when dealing with this, so we'll say that the sum of all of the forces is equal to negative our spring constant, negative K, multiplied by x minus x0. Okay, where x0 is the point at which our spring is limp. Okay, it's not being stretched and it's not being compressed. Okay, so it has no forces acting on it. That's our x0. And our x is our displacement. Okay, so our distance pulled from a certain point of reference. Okay, and this is of course going to be equal to our mass multiplied by acceleration. Now because we're dealing with, over here we have our variable x, okay, which represents our displacement, so we're going to use the second derivative of our x, okay, x double dot, and this is our acceleration. Okay, you'll see why we write it like this. Okay, so this equation is the equation for harmonic motion. It's very important. Please write this down. Another name for this equation, or the type of this equation, is that it's an equation of motion. Okay, so equation of motion. Now, an equation of motion is any equation that has the variables of acceleration, okay, so here we have x double dot, that's acceleration, or velocity, or displacement, okay, x is displacement. And it can also have two of them, or if you find something with three of them, it doesn't matter. Those are equations of motion, and this equation describes harmonic motion. So if we have a harmonic system, this equation will describe its starting position, its velocity, and so on and so forth. Another useful trait of this equation is that if you get a question in which you're asked to prove that some system is working with harmonic motion, if you can get the equation of your system into this type of format, then you can know that the system is in harmonic motion. Okay, so our equation over here has to be in this exact format. Okay, so what does that mean? That means that number one, this negative must always be here. Okay, always, always, always. Number two, that means that our k and our m are positive constants. Okay, so this is a const. Okay, and it's a positive, and also this is also a constant and it's positive, and we must always have our x0 here. Now our x0 can be positive or negative, okay, but it's also a constant. But this can be positive or negative. It's the only difference. And it must always look exactly like this. Okay, so you'll notice that we have here our x, and here we have an x double dot. So that means that this is a differential equation, and the answer to this differential equation, which if you want you can solve on your own, is going to be our x as a function of t, so our displacement as a function of time, is going to be equal to a cosine of omega, okay, angular velocity, multiplied by t, plus phi, and then plus x0. Now, a lot of teachers or a lot of professors will omit this x0. I think that it makes it more clear and it's a more accurate answer, so you can write it if you wish. Now, this equation is called the general solution to this differential equation. Okay, so this is the answer, and now let's take a look at what this means. So we can see that our variable is t, okay, so we have a t over here and a t over here. Okay, this is the variable of the equation. And now we have all sorts of constants in here. We have our a, we have our omega, we have our phi, and we have our x0. Okay, so now what we're going to do is we're going to take a look at what each of these values means. So let's deal first with our x0. Now our x0, over here we said that this is where our spring, okay, doesn't have any forces acting on it, okay, it means it's limp. So, but here when we're saying it, we're speaking about the point of equilibrium. Okay, where the forces are balanced. So it's not necessarily limp, but the forces are balanced. So point of equilibrium. Now, the definition for finding your point of equilibrium, it's where you get that your sum of all of the forces is equal to 0. Okay, so that's the sum of all of the forces, not just the force of the wire, okay, or of the spring. So the sum of all of the forces is equal to 0. Okay, and this, our x0, is very easy to find because we'll know what this is in the question. Okay, we just take this x0 and plonk it over here. Okay, so the next thing I want to know is what is my A? Okay, so my A describes my amplitude, okay? A for amplitude. So what in fact is my amplitude? My amplitude is the furthest distance away I can get from my point of equilibrium. Okay, so let's say my point of equilibrium is here, x0. So that means that from this point, I can go this distance, A, okay, up until here. And similarly, I can go the exact same distance up until here, okay, but minus A. Okay, so I can go A to the right and minus A, which means it's going to the left. And that is my amplitude, the distance I go away from my x0. Now, in harmonic motion, this is very important because the whole point is that my mass is going to be moving in harmonic motion between these 2 points. So I'm moving periodically between A and minus A. So let's just show you what that means. So if I'm starting, for instance, at A, and I go from A to minus A, and then back, okay? So that is 1 period. Okay, so this blue line, starting from here and going and also ending at the same point, is called 1 period. So if that is 1 period, then we can say that my frequency is going to be equal to 1 divided by t, okay, which is my time for 1 period to be completed. Okay, so my frequency is the amount of periods I have in 1 second. Okay, now notice this is a capital T, so it's different to this T over here. Alright, so our frequency is the number of periods per second, and it's equal to 1 divided by T, which is our T, this over here. So this capital T is the time I wrote with a capital T, okay, to differentiate from this time over here, to complete a period. Okay, so 1 period. Alright, now the next thing that we have are omega. So I'll write this up here. Now our omega is equal to 2 pi f. Okay, where f is our frequency over here. Okay, so this is frequency in radians. Okay, so I've highlighted this f over here so that you can connect it to what is over here. Okay, now the next thing that we have is our phi over here, and it has something to do with our initial conditions. Okay, so where our system starts its motion and so on and so forth. Okay, so now over here we have our equation for our omega, okay, over here. So now let's see how we find what our omega is. Okay, so we have our equation, which is that omega is equal to the square root of k divided by m. Okay, so where our k over here is the coefficient of this, of our term x minus x0. Okay, so this over here, this green, this is our k, and our m is the coefficient of this term where we have the x double dot. Okay, so it's our greens. Okay, so this green highlighter over here is to remind you that it's these coefficients. Okay, then our next thing that we can look at is our A and our phi. Okay, now our A and our phi are both dependent on our initial conditions. Okay, so the way that we do this is that we find our position at t equals 0, and we find our velocity at t equals 0. Okay, so our initial position and our initial velocity. And then through this, we'll be able to find out what our A and what our phi is equal to. Now notice that our omega is dependent on constants, okay, on our k and on our m. Okay, so that's the physics or the building blocks of our system. Our A and our phi is dependent on what we do with our system. If we begin with the spring stretched a lot or stretched slightly, okay, and this is given to change. Okay, so with that, depending on how I begin my system, if it's stretched a lot or a little, my A and my phi will change. However, my omega will always stay the same. Okay, so my omega, even if I stretch my mass up until here, or I stretch my mass up until here, or I compress my mass, my omega is constant. Okay, so to sum up, how to work out questions dealing with harmonic motion. So the first thing that we do, force equations, then once we've written that, we sort out all of our variables into this format, okay, for the equation of motion when dealing with harmonic motion. Then after we've done step number 2, okay, so then we write out our general solution. Okay, so we solve for x of t. And then, once we've done that, then we have to find out what our A, omega, phi is, and our x0 is obviously this x0 over here. Okay, so then we find the constants. Okay, so omega, A, and phi, which we saw our omega is this, and our A and phi come from our initial conditions. Okay, that's the end of the introduction.